All right, good morning, everyone. Today we have Dr. Ahmed here for the presentation. He's a geophysicist with over 30 years of experience in research industry and academia. He's the president of Maxima Geophysics and an adjunct professor at Oklahoma State University. His active expertise includes seismic, electrical, magnetic, and ground-penetrating radar methods for environmental and engineering applications. Dr. Ahmed has completed more than 90 geophysical projects worldwide and has authored over 100 peer-reviewed papers and abstracts. He is a recipient of the AAPG Inspirational Geoscience Educator Award. Welcome.
Okay. Good morning, everybody, and thank you for having me here, and thank you for your kindness to allow somebody who is not fully authentic engineer coming from some different field to hold you hostage for 30, 40 minutes. It's so kind from you. However, yes, we're not fully authentic engineer, but we do what we do for engineering. Actually, it's a geophysics for engineers. And I'm here today trying to convince you, hopefully I can do that there is something called the geophysics that I'm sure that most of you are familiar with, that can help you at some point reduce the cost and the risk. Two big parameters that every project manager is interested in reducing. So thank you again for the team who invited me, and thank you for, I'm just trying to get to the presentation screen. Okay. So thank you for the team who invited me, and thank you for people who made it at this early time in the morning at 11, and thank you for those who are joining online, and hopefully we'll have some time after my short talk for questions and the communication, because communication actually is the main factor that I'm trying to enforce or emphasize here. When you are engineer and trying to deal with somebody who's not engineering, coming from different world, using a different technology, but serving you, the communication is a key factor. How we can ease this communication and how we can understand each other to get the best benefits for your engineering project. Okay, thank you. So again, my name is Ahmed Ismail, and this May, actually, it's going to be my 30th anniversary of project experience. I do this geophysics for my life, my entire life. Actually, my first project was in 1996 in May. So in next May, I would have completed 30 years of experience in a geophysics project, and I would love and always love to talk about this experience with different communities. I give many talks at many events, and talking to engineers actually is one of the best communities that I would love to talk to, because engineers are practical people. When we speak, we need to get benefit out of what we are presented. So my talk today is briefly about a definition of geophysics. If you want to define geophysics, you might have 10 definitions of geophysics depending on whom are you speaking to. So we're going to give just a simple engineering definition for geophysics, how it works. And then usually I give 6 case studies, but because the short time of today's talk, we're just going to reduce it just to 3 case studies, very briefly case studies, then talking about the strengths and the limitation of the geophysics. Geophysics is magic, but it's not always magic. It has limitations. And the cost. Then will elaborate on how to communicate as people coming from two different backgrounds. Are you guys okay with that? Shall I continue or shall we stop here? Continue. Okay, thank you. Okay, geophysics. Geophysics is simply we do a job like radiologist in the hospital. When you go to visit a physician, the physician wants to run a surgery, and he doesn't want to get into our bodies unless he image our body and know where is the problem, the size, and the severity of the problem before he or she interfere and do the surgery. The radiologist in the medical field is exactly the geophysicist in the engineering field. Before you go and interfere and you do your design and bunch the ground with holes and the trenches, it's better to get an image of the subsurface. So we do an image, like X-ray image. What other image? MRI, yeah, the expensive one, I hate it. The MRI image. We have these different type of images, and they are also different in prices based on the quality that you are looking for. So the simple definition of geophysics is imaging the subsurface. We're not imaging the body, we're imaging the ground subsurface. We are successful to get an image of the subsurface if we have contrast in the physical properties. Physical properties like density, like magnetic, like electrical conductivity, like seismic velocity. If the ground is composed of materials like this model here that has clay over limestone over sandstone, these materials are different in physical properties. Engineers like what? Like density, correct? Clay is different from limestone in density. Clay can pass the electric current way better than the limestone. So clay has different electrical conductivity than the limestone. So they are different in physical properties. Yeah, we're happy geophysicists, so we can create a beautiful image for the clay versus limestone in our geophysics image. So we are images generator people. Okay, how it works. This guy actually did very nice experiment. This is an outcrop, by the way. It's a poor quality picture, but it's rarely that we do that. This guy has a limestone outcrop, and it doesn't have layering, but it has like interface between the different blocks of the limestone. It has some gray limestone versus yellowish limestone that could be sandy limestone. And he ran ground penetrating radar, one of the geophysical techniques, along this outcrop to see how this geological image look like in this image before the GBR image, the geophysical image. So this is a ground reality. This is the image. So this is the image. What do we do with this image? Look at this image. I want you to put the head of the geophysicist and look at this image and assume that we don't have the geology. We don't know anything about the subsurface. Can you pick any information out of this image? Definitely, yeah. When you see an image like this, when you see something linear, very consistent like this, so it's interface between two blocks of rock up, rock down. The same here, the same dipping feature here. If you see the signals has high amplitude here versus washed out here, it has a meaning for us. So we geophysicists, we know the image. We spend our entire life looking at these images that doesn't make sense to you, but it makes sense to us. And we drive interpretation of this image and provide it to you in our geophysical report, geophysical/engineering report. But we are careful. We call it interpretation. We haven't seen it. We just imaged it. And out of the image, we're trying our best to come close to the ground, the true ground. But because we haven't seen the true ground, so we are interpreting our image to come up with something like this. And this is why in every geophysical report you receive from geophysicists, you find a section called geophysical interpretation. Okay? And the interpretation, guys, like when you talk to somebody and you say something which is confusing, you say, can you please explain this to me? Explain why. Why you say, ask somebody to explain something, because it could have different meaning. Our interpretation also we could have different interpretation. So don't take what we say to you as 100% correct. If it contradicts your ground truth, stop. Say, hey, 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 stop here. No, 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 no. This layer doesn't exist. Oh, I'm sorry. This is my interpretation. So get me your ground truth, and I am gonna readjust my interpretation. Okay? So it's not a conflict, but it is just working together. Okay. Stories. Are you guys ready for just some short stories here and there? Okay. Okay, story one. In St. Louis, I-44 in St. Louis. This is one highway, this is another highway. They were generating a ramp between the two highways. The machines were there. It was heavy rain overnight. They have this nice, beautiful sinkholes collapsed almost 100 feet diameter and 50 feet depth. Good news or bad news? Yeah, you're engineers. Bad news. For us, it's good news. No, I have to hide this happiness, okay? I have to pretend that I'm sad, okay? Oh, what happened, guys? Sinkholes. Yeah, it's a risk even to get the drilling rig there to put the ground everywhere to see if there are similar ones, not collapsed yet or not. And even this one, they want to go below it and see if it has something even below it can collapse later or not. So it's a long story of risk after risk after risk. So simple answer is, get me an image 50 feet down to the ground, continuous, so I don't miss one, and safe, non-invasive, so I don't risk the machines, the rigs. Who can do that? The geophysics, definitely the geophysics. In environment like this, I want you to think as a geophysicist. When you have a sinkhole in a body of limestone, sinkhole is a vacuum. It could be air-filled, water-filled, clay-filled, correct? If you have a sinkhole, air-filled, water-filled, clay-filled, is this filling material different from the limestone or similar to the limestone? Completely different from the limestone. If it is completely different in physical property, it makes my life very simple in geophysics because it's going to be so easy for me to see it. And actually, it was. So you run a simple technique called electrical resistivity, the reciprocal for electrical conductivity. Electric current, when it tries to go through the limestone is resistant rock. If it is competent, if it is confident limestone, it doesn't allow the electric current to go through it very easily. But when the when the sinkhole is filled with water, electric current loves water. It goes very quickly in the water. Okay, so my electric current to try to go through the limestone. This red means the high resistivity on the scale. So it tried to go through the limestone. The limestone is resisting until we got to this point. Electric current was easy going through this local feature. So this local feature will be a sinkhole filled with what? Air? No. Current doesn't like air. It's either filled with water or filled with clay. Very simple. Very simple. Look at this one. The red is the high resistivity, the nice competent limestone. So this is our bedrock. The blue is the very low resistivity. Somebody is not happy with the interpretation. Okay, we can discuss this during lunch. So if you have low resistivity here, very low resistivity within the limestone, what does it mean? It's another sinkhole either filled with water or clay. So bottom line, I'm not going to explain the entire project. I have tons of data for this project, but bottom line, with non-invasive continuous image, you can clear the site if it for sinkhole presence very easily, very safe, and down to tens of feet. Okay. Okay. Since you guys like the sinkholes, since it's bad news for you, I'm going to give you even more bad news, okay? Another project, but it wasn't close to a highway or roadway. It was close to a railway track. It's a freight railway track in another country. I'm not going to mention the name, but the railway track is here, and I put it as this dashed line in this bottom image here. And look at the environment around it. There is an artificial recent lake on this side. There is a palm tree field in this side. These grays are developing sinkholes. These are some of them. Nice sinkholes, very deep ones, more than 100 feet deep sinkholes. So the government was shocked. Come on, if one of those sinkholes develop under the railway track will shut down. And if the railway track shut down for 1 day, it costs them over 3 million per day, almost. So imagine if it shut down for a month. So everybody was shocked. Come, clear the site. If sinkholes are developing here, it might migrate to below the railway track. So we need to clear what is below the railway track for the presence of sinkholes. We can put this distance is 4 kilometers. In order to clear it, I would assume that if we put a borehole every 20 meters to make sure that we're not missing any sinkhole, so we need 2,000 borehole, correct? Oh my God, 2,000 borehole is a lot. Time, money is a lot. So we need an image. We need somebody to go non-invasive, fast, and cost-wise, low cost-wise, to clear the site for sinkholes. It's a geophysics, definitely. But because this project is sensitive, budget is very good. They give you money to do whatever you want, actually, with geophysics. So instead of using just one technique, we multiply three, we add 3 images, 3 techniques. It's something in the geophysics. It's like if you want to know somebody more, take a photo for him or her from different angles with different camera. Take a photo facing them, a photo from this side, a photo from this side with different camera resolution. Put the 3 together. Oh, this guy looks so and so and so. Correct? We do like this in geophysics. We integrate images. So the top image is seismic reflection image. Seismic reflection is very good. We are after sinkholes. Main question, is there any sinkholes along the railway or not? So this one clears. It shows the bedrock very well. It also shows if we have any faulting in the area, because fault was a possibility in this area. It's a graben, and we can have a smaller fault intersecting the railway track. Another image, it's called the shear wave velocity image. It shows the strength of the materials. Yes, it's only 25 meters, but it's a very important. A third image is electrical resistivity image. It shows the water content and the clay content. We picked over 10 features. These numbers are the features that correlate between one image to other. Just giving just one example, look at image at feature number 4. Look at this ball feature, at this feature, at this feature. It's a layer, almost 1 kilometer length of almost fine sediments, clay, silty materials. Their thickness is over 50 feet. Things are changing rapidly very much. Yes, there are no sinkholes. Bedrock are not faulted. Good news for the organization. But bad news, your near surface, your upper 150 feet is horrible, terrible subsurface. And we recommend it for them to indeed move the railway track. They keep resisting, but this is our recommendation. Okay, it seems that this case made everybody mad at me, but that's fine. I'm going to take it. Okay, I'm going to shift away from the sinkholes. I'm going to assume that we have roadways, that we have filling materials on the top of the bedrock, and based on I'm just extracting these images from different projects. We want to inspect the bedrock for multiple reasons. We want to wanna image the topography of the bedrock, wanna image the integrity of the bedrock, wanna image the rippability of the bedrock under roadways. I'm gonna share with you a very quick image, but I need your help with these images, guys, okay? Image number 1. Do you like the colors or not? Very beautiful image. This is called the seismic shear wave reflection. I know that you're going to forget these names after lunch, but try to remember as much as you can. Shear wave reflection image. The blue line is Mr. Bedrock. This is the depth in meter, 40 meters. This is the distance over 1 kilometer length, 40 meter depth. And this is how the bedrock behave. It was like at 30 meter depth, most of the line, and then suddenly it rises up very close to the surface and it came back again. Very much unexpected behavior from the bedrock in this area. I'm not going to talk about the engineering impact. It's you. I'm not going to talk engineering here. But this is how the bedrock behave based on this image. Another image. Yeah, it's a blurry, it's not good quality image, but it was shock for us. This is P-wave reflection image. It was a roadway along an earthfill dam on the top here, and this is the bedrock. This is the foundation rock of the earthfill dam. It was very nice rock everywhere, very nice rock, but the bottom layer of this rock, we suddenly found this behavior. What is that? What is this, doctor? What does this mean? This is deformation in the bedrock. It could be a secondary fault from a major fault somewhere. It's an earthfill dam, and you have a couple potential faults crossing the bedrock. It's a very bad consequences, correct? Again, it's out of this image. Another image. I think you like this color, red and the green, correct? So this is velocity image, shear wave velocity, not reflection image. It was in St. Louis. They drilled in I-72 in I-70 in St. Louis, major highway. They put few boreholes. They were not happy with the integrity of the bedrock. They say it's a very highly weathered bedrock, potentials for sinkholes, blah, blah, blah. So we need to image we need to get a continuous image that reflect the integrity of the bedrock. Very easy. Yeah, get shear wave velocity image. Look, this is a dotted line is the bedrock surface. This is the shear wave velocity. The red is low, the green is high. You guys are the engineers. If this is the top of the bedrock and the velocity is low within the bedrock, like this, like that, is this good bedrock or bad bedrock? It's weathered bedrock. It's weathered bedrock. The shear wave velocity is very high here. It's a competent bedrock, but in an area like that, yeah, shear wave velocity is random and it's very low within the upper 20 feet of the bedrock surface. So it's a definitely highly weathered bedrock. One last image. This is only for rippability. They want to do some engineering work here, and they want to inspect the rock rippability. So it's easy to generate such a kind of P-wave velocity image, and you draw the contour. This 8,000 feet per second the contour line represent the non-rippable zone. Very easily that you can know if the rock is rippable like the red and the green, or non-rippable like the bluish color here. So bottom lines, thank you for the technology. Getting long image, big size images for the subsurface down to tens of feet, even along asphalt like here, or along roads like this, became even way faster and easier and less expensive than before because of the technology that we called land streamer in geophysics, that you hook your receiver into the car and you drive the car and you stop every, say, 10 feet. You take a measurement then you drive, stop 10 feet, take a measurement, then you drive 10 feet, you take a measurement, and at the end of the day, you can acquire up to 3/4 of miles of day from this data or 2 miles from this data in one day, and in 3 days, you can generate a full image for the subsurface down to tens of feet. Look at the subsurface here, look at the subsurface here, look at the shear wave velocity and the subsurface right here. A full image in less than a week because of this. Yes, sir. No, 3 different methods, 3 different roads, 3 different images. Yes, yes. Okay, enough roads, enough sinkholes, enough bad news. Let's share some another bad news. Okay. Seepage from dams. I was in a big meeting and I heard this statement: every dam leaks. Is that correct? Correct? By design. Okay, that's a fair answer. Okay, I haven't even invited to a healthy dam. Every dam I invited to was leaking. But anyway, seepage here at the bottom of the dam in Oklahoma, but the suspect either the body of the dam, because the seepage is observed here at the footage of the dam, the body of the dam or the abutment or the natural rock. And based on who's the cause of the seepage, the fix is different. You are the engineer. You know the fix. If the natural rock is different from the body of the dam, is different from the abutment. So how can we locate the seepage location? If we drill everywhere, unless if we put like 100 well up and down, and you know drilling on earth-fill dam is very restricted actually. It can actually compromise the safety of the dam. So drilling here is very restricted because not to compromise the safety of the dam. So we need an image. We need to request an image for the dam. We need to locate where the seepage is coming from. Body, natural rock, abutment. We need to identify this. Very simple technique established like almost 90 years, 70 years right now, is called electrical resistivity. You're all aware of. It knows where the water is highly saturated in a place versus a dry place. So you run parallel lines along the dam and you get multiple images like this. And within these images, you get these zones, the blue zones, guys. High water saturation here and there. So you plot them here and you tell the guy, these are the potential seepage area. And I mean to put the potential because it could be just places holding water. But is the water really moving, seeping or not? We're not sure. So we call it potential seepage area and we'll stop there. The same client came later and say, hey, I have, for some engineering purpose, the water in the reservoir is going to rise 20 feet over a month. Can you come and monitor? Put your machines on the ground, put your sensors on the ground. And while we are rising the water level in the reservoir, tell me at which water level the seepage start and where, at which location it starts and continue. It's called seepage monitoring. It's called the time-lapse measurement. We were lucky to have this because this is 100% proof where is the seepage start, at which elevation of the water level, and where is the seepage pathways. So look at this, and let's explain it together. These are differences between the measurement. So if you measure today and you measure tomorrow and you subtract the two measurements from each other, if the result is 0, so there is no seepage. If the result is this blue thing, it means there is a seepage here. This is the elevation of the water. This is the date where the measurement is taking. We measured for a month, but we just selected some few days to present in one slide. And look at the elevation versus the seepage. At this elevation, the seepage was very small and right here. When water rises more, it spread out. When more, it spreads out. More spreads out more, it even goes to the natural rock. So exactly locating where is the seepage start, at which elevation, at which, by rising the water in the reservoir. So I'm gonna stop application here, and I have just like 5 minutes. Strengths and the limitation. Geophysics is great. It can provide you with a very long image at a shorter time. It's safe, it's non-invasive. However, geophysics doesn't do everything. Sometimes you get wrong interpretation. You have to challenge the interpretation. The measurement is not wrong. The image doesn't lie. It's just our interpretation is not unique, because one feature or 10 features can give the same response on the geophysical image. So there is nothing wrong here. It is just reading the image is misinterpreted. So if you get a misinterpreted image, go back to the geophysicist and let him or her adjust the image. It requires boreholes. Geophysics will never replace the borehole. Look at this very nice image here. This is a resistivity image, almost 150 feet depth, 1,000 feet length. Very beautiful layering. But is this layer clay? Is this silt? Is this groundwater? I don't know unless I put a borehole here. Without a borehole, you get with million interpretation. You have to constrain the interpretation with a grounded truth. My message to all of us here is about the cost. And I want to warn you about the cost. As engineers, cost and risk is very important factors to you on your budget, correct? Yes. And for the same project, you can ask a geophysicist and tells you, yeah, this will cost 50,000 in order to resolve this sinkholes in your site. 50,000 is too much. You talk to another geophysicist and say, oh, I can do it for you for 15,000. Definitely you will go with the 15,000. Why shall you go with the 5,000 one? Appreciate this one, you get very mad at this one, and you get very happy with that 15,000 one. But it's not fair comparison, my friend. You don't know the details. This guy will put 24 lines, so he or she will not miss anything. This guy will give you an image, but based on just 6 lines, will do very little, and they will give you an image. We're both looking for something that we're not sure if it's there or not. So I'm giving you an image, I'm giving you with 50,000, I'm giving you a similar image with 15,000. Definitely you're gonna buy the cheap one, correct? Cheap one doesn't have as much detail, it's just a common sense, as the expensive one. So you're gonna turn out mad at him or her again. Bottom line, communication. If you're talking to a geophysicist, describe the problem, describe the budget, describe the logistics, describe the goal of the project. What you want from the geophysicist to give you something that you understand, not just colorful images. Give you alternative. Doesn't say, and you can hear this from many geophysicists. He or she does seismic, and anything you ask for, you say, oh, I'm going to do seismic. I'm going to do seismic. No, 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 no. I need alternative. I need cost alternative, imaging alternative, schedule alternative. So speak with different geophysicists to give you different alternative. Okay. My last advice for you, to take it before lunch, make a geophysics friend, somebody that you're comfortable with. Don't buy from him or her, just ask him or her about things. Okay? So make a geophysics friend, ask him or her about things. He or she can save you a lot, actually, and can save you from a lot of risks. I'm going to stop here. Once again, thank you so much for your patience. You guys are great. Appreciate it. Thank you. Yes.
So I haven't seen much on like tunneling. I've seen a lot of GBR, but I haven't seen how do you do geophysics for doing a tunneling.
Yeah, it depends what do you want to do with tunnels. I said I have 6 case studies at the beginning, but I just presented 3 case studies because of the time. But I have another 3 case studies. The GBR case studies that I'm presenting here about bridge deck inspection and the concrete inspection, not about tunnels even. But it depends on what you want to do with tunnels. If you want to see the tunnel itself, that's a very straightforward application. If you wanna characterize the ground for establishing a tunnel, it's way more than the GBR. You need some other parameters. You can't get it from the GBR, so you do extra work, 2 extra steps. You do seismic, you do resistivity to get a full characterization. But I mean, tunnel studies, either to put a new tunnel or to image an existing tunnel, it's like a classic application in geophysics. Yeah. That's a very good question. GBR, for example, is very good technique, continuous. You can see the results in the field, but you're limited to a max of 10, 15 feet at the most. If you're lucky, you can get 15 feet. But with the seismic reflection, you can get 1,000 feet. However, the details that you're going to see in the 1,000 feet are not similar to the details that you see in the 15 feet. This is contradiction. If you want to go deeper, you're going to see less details. If you want to go shallow, you're going to see very good details. This is why the GBR is used to see corrosion in the repairs, very millimeters scale features. Seismic reflection, if you want to go deep 1,000 feet and you're telling me about a feature 1 meter by 1 meter, I would say, no, I'm not going to see it. So if you want to go deep, you can go deep, but you're going to miss the resolution. Thank you. No, it's a filling reservoir. It's a hydraulic filling. Yes, correct. Yes, it's controlled the filling. Yeah. Yes, time series resistivity. Yeah. Yeah. We left it on the ground. No, we left it on the ground because we left it in the same place, same condition. Everything is the same, so we can do the time lapse. You have to fix everything. We rented equipment, tons of equipment. We put it 4 lines on the ground and we left it for a month. We put a guy on the hotel near there. He just carries a machine, go every day in the morning, take a measurement. Second day in the morning, take another measurement and do the difference. Yes. For the sinkhole? For seepage? Oh, yeah. Oops. Yeah. You said the size? Yes, electrical resistivity, yeah. That's a very good question. Yes. That's a very smart question. Minimum resolution actually depends on many factors. As you said, electrode separation. We were using 1.5 meter there to get the best. But the problem when you minimize the electrode spacing, you lose also the depths. So we kind of compromise. And definitely the guy who's looking for seepage, if we tell them, yeah, the seepage is happening within 15 feet. It might be happening in the center of the 15 feet. It might be happening in this side or that side. So it's not exact, but you give him the zone, the pathway. Yeah, you're absolutely right. The resolution is not exact resolution. Yeah, you're very welcome. Yes. Oh, that's a very good question. I love this question because this goes on a discussion on the phone between you, engineer, and the geophysicist. You have the problem, but you're not a geophysicist. So you say, hey, I am going to a site, but this site is karstic site, and I might have sinkholes. I want to image them. So the guy is all about money. Geophysicist is greedy, actually. He want to make money. We'll ask you, okay, how deep? Because the deeper you want to go, the more cost. Okay. How small? The smaller you want to see, the more cost. Okay. Other thing, how's the field condition? If it is very nice open field, it's less cost. It's a forest, a jungle, it's a high cost. Methods, once we agreed on the conditions, the depth, the size, the resolution, and we took these factors factored into the cost, we come to the method. Some methods are very cheap, like radar, GBR. I found that you're just aiming for 15 feet, 10 feet, and you want to see small things. Oh, GBR. In GBR, I can cover a mile per day in GBR. So very, very, very minimal. No, I want to see at 50 feet depths. That's a different story. I'm going to put resistivity. It's a lot of electrodes, a crew of 4 or 5 people. My productivity is almost like 500 feet per day. So cost is going to rise up. It's 100, 200 feet depths. So resistivity will not capture it. I'm going to put seismic. Seismic is even more expensive. So the cost, this is why I'm saying when you talk to the geophysicist, tell him the target and tell him this is the amount of money that I have for you to play with. So he will design for you. It's like in a shop. I can design for you anything based on your budget. Actually, you can do a project for 5,000 and you can do a project for 500,000 based on exactly how is your budget. Things can tweaked around this budget.
Some people say, well, it's not going to detail.
I was clear with you, and it's up to you to make the decision. Yeah. The cheap one will not give you the details. Yeah.
In lines, much more reliable. Yeah. When, even if it's just one of the physical methods is so more. Seems like that would, since you're working on interpretation,
Perfect.
gives you more confidence.
Limiting is uncertainty because there is a big thing in geophysics called uncertainty, non-uniqueness. To restrict this, to limit this, you allow me to do more than one technique. Or you put more instead of no boreholes, you put 1 or 2 boreholes. Give me either ground truth or allow me to put more techniques. This is the only way to restrict or constrain the non-uniqueness in or uncertainty in geophysics. But I mean, what I'm trying to say, it's a common sense. If you want to see more details, you have to spend more. If you want to get reconnaissance survey, like we can do 2 miles of data and provide you 2 miles of data in 5 days. But it's a reconnaissance. You can't rely it on a to see a sinkholes. It just to show you how the bedrock behave up and down, how the competent is the bedrock, but it will not see the fine details. It's a reconnaissance survey. Thank you. Thank you so much for having me. I appreciate it. Thank you. Appreciate it. Thank you. Thank you.